Good morning. Today I'm going to go over the free body diagrams. A good, helpful website to go to is the physics classroom. And if you look up Newton's laws or free body diagrams, actually, it'll give you the answer to some of these, and it actually has new questions for you as well. So I'm just going to go through some of these and show you how we draw our free body diagrams. If you look up here, we have the different types of forces that we could have. For example, we have the force of gravity. So when we put the subscript down here, we just put force of gravity. This is the normal force. This is the applied force. We have frictional force. We have like air resistance or wind resistance force. We have a tension force. So we're just basically labeling the different types of forces that we have. So if we take a look at the very first one, it says a physics book rests upon a level table. Well, if we just draw in a table, we'll just have this horizontal line represent our table, and this box represents, or the square represents the book. We can say it rests on the table. So we already know that the force of gravity is actually being applied to this object here. So I'm going to draw in a vector arrow. This vector represents magnitude and direction. It's pulled in a downward direction, and the magnitude has some unknown magnitude, but we can draw some arrow in. And notice that we're drawing the arrow from the center of mass of the object. So why doesn't the object fall through the table? Well, there has to be some force that's actually pushing back up against the book, and there is, and that's called the normal force. Now, if you notice, I drew the magnitude of the normal force about the same as the magnitude of gravity. So the vectors are the same length, which represent the same magnitude, and they're in opposite direction. So when we look at these, we could say that these two cancel out because we subtract the vectors whenever they are in opposition to each other. So they're opposite to each other, so we're going to subtract. And basically what we get is that the sum of all forces equals 0. Sum of all forces equals 0. That one's pretty easy. There's only two forces that are actually acting on this object right now. If the sum of all forces equals 0, we know that there is no acceleration, because the idea is that if you have some force, that force causes acceleration. But since the sum of all forces equals 0, there is no acceleration. So it can do one of two things. It could be at rest, or it can be in constant velocity, be at constant velocity. And here we see that the book just rests on the table. Let's take a look at the next one. A skydiver is falling and has reached a terminal velocity. Right off the bat, we know terminal velocity, that's the highest velocity that an object can reach while it's in free fall. Terminal velocity could really mean constant velocity. And so if we have a constant velocity, then we know that we're going to have an acceleration of 0, because constant velocity means that we are not changing our velocity. So acceleration is 0. So we know that acceleration is 0, which means that the sum of all of our forces is going to have to be 0. The sum of all our forces has to be 0. So we have a skydiver falling and has reached terminal velocity. We know that the force of gravity is acting on this, and again, the square represents the skydiver. So the force of gravity acts on the skydiver, but there has to be some other force as well, because we know that the sum of all forces has to equal 0. And so we know that there is wind resistance or air resistance or friction due to air. We could go ahead and put a frictional force here, because that's really what it is. A frictional force opposes motion. So a force of friction in the opposite direction. Notice that the magnitude of the two are the same opposite direction, so they're canceling it out and makes the sum of all forces come out to be 0. And that's really all that's acting on the skydiver. Now if we look at the next one, a large crate is being pushed left with a constant velocity. So again, constant velocity, we can use this idea over here that constant velocity means that you have an acceleration of 0. Sum of all forces is going to be 0. So all of our forces have to add up to be 0 when you're at a constant velocity. So let's look. It's being pushed left. So there has to be some applied force. There's an applied force. We know that the force of gravity is acting on all objects. And since it is on some surface, we are now going to have a normal force. Let me go back to this. We weren't on a surface here. The skydiver was not on a surface, so there was no normal force. Right? The force that acts perpendicular to the surface on which the object is placed, since this is not on any surface, then we don't have a normal force. Notice here it was on a surface, so the normal force acts perpendicular to that surface, and same thing here. The box is on some surface, and so a normal force acts perpendicular to that. Now, normal force, force of gravity, they're going to cancel each other out. So we have an applied force. We said earlier that it has a constant velocity, so the acceleration is 0, and the sum of all forces has to be 0. So that means that we have to add another force here. And what's the force that opposes all motion? Well, if we know that we have motion to the left, the force that opposes all motion is the force of friction. I slightly drew this a little bit too big, but these two vectors should be the same magnitude, so they cancel out. These two forces should be about the same magnitude, and they should cancel out, which would give us sum of all forces equaling 0. And that is the case. They cancel each other out. So we have a constant velocity. The next one, a sledder has reached the bottom of a hill and is coasting right to the right while slowing down. So he is slowing down. So if you remember what constitutes acceleration, we could have an increase in speed, we could have a decrease in speed, or we could have a change in direction. If it's slowing down, we have our decrease in speed, which means that we do have some type of acceleration. And what is it that causes an acceleration? We know that we have to have some force acting on that object. So let's figure this out. We know that we're going to have some force greater than 0. So the sledder's reached the bottom of a hill. So it's at the bottom of a hill, which means that it is on some type of a surface. So we should know at this point we have the force of gravity. We have the normal force acting on that, and so we know that these are going to cancel out. And it's coasting to the right. If we say that it's coasting, that means that we don't have any type of applied force that's pushing or pulling that sled to the right. It's moving without having a force applied to it. Now it's slowing down. What causes all objects to slow down and eventually stop is the force of friction. So we know that it's moving to the right, and what opposes all motion, it's the force of friction. So we have some frictional force that opposes motion. We know it's moving to the right. It opposes motion, so it would be going to the left. So the force of friction is to the left. No applied force means that if these two cancel each other out, the only force that's unaccounted for is this force of friction, which is opposing motion, and will cause this to slow down. So we do have some force. So the sum of all forces is going to be something greater than 0. We don't know what it is, but we know that it's greater than 0, which means that we do have acceleration. We can do another one. Ball moves up, ignore air resistance. So automatically we know that we have force of gravity. But we know it's moving up in the air, so it's not on a surface, so we don't have a normal force. We don't have an applied force. We're ignoring air resistance, so we're ignoring the frictional forces, so we don't have a frictional force as well. So looking at this, the only force that acts on this particular object is the force of gravity. an air track glider. Let's skip that one. Let's go to this one. Brakes are applied to a right moving car skids up. So it's on the surface. Right, the car is moving. So we have the force of gravity. We have our normal force. Brakes are applied. It skids to a stop. So there is no applied force. It's moving to the right, but there's no applied force. We have frictional force of the brake. So the friction between the brake and the tire causing its opposing motion, so we have a frictional force. So these two cancel out. We have a frictional force that's unaccounted for, so that means that we have summation of all forces is greater than 0, which means that we have some type of acceleration, which if we look up here from earlier, acceleration would be a decrease in speed, which is what we have because it's coming to a stop. It has to slow down to come to a stop. So we do have acceleration, and that acceleration is a decrease in speed due to the frictional forces of the tires. So a spider slowly descending a thin silk thread at a constant speed. Now one thing that we haven't talked about is a tension force, and tension force is just the force that would be found in a rope or chain, something that's hanging from one of those. So silk thread, if the spider is on that silk thread, it's slowly descending at a constant speed. We know that the force of gravity acts on it. It's not on a surface, but it is hanging by a rope. So here's, or thread. So here's the thread that it's hanging by. There is tension in that thread, so the force would be a tension force. So the force of gravity and the tension force, they cancel each other out. They're going to cancel each other out. And so we have a constant speed, so we know that the sum of all forces is 0. Constant speed means that the sum of all forces equals 0. We cancel each other out. And so acceleration is 0 as well. Do one more with tension here. An elevator is rising at a constant velocity, so constant velocity tells us that the sum of all forces is going to be 0, which means that we have 0 acceleration. So it's not touching the floor, so it's not touching anything. So we have the force of gravity. We do not have a normal force, but we know that the elevator is hanging by some cable. So here's the cable. And there has to be some tension in that cable, so the vector that I draw is the tension force found in that cable. So force of gravity, tension force, they have the same magnitude, opposite direction. They cancel each other out, which means the sum of all forces is 0, and we can see that the acceleration is 0. If you need help with any of these other ones, you could come in and get help, and I'll help you with that.